All right. Hi, everyone. I'm Justin Essery. I'm an associate professor here at Rice University. Welcome to the International Methods Colloquium. The International Methods Colloquium is a periodic online interactive seminar discussion on the application of quantitative statistical methodology to the social sciences, sponsored by Rice University and the National Science Foundation. This week's speaker is Erin Hartman from the University of California at Los Angeles, and her talk is entitled An Equivalence Approach to Balance and Placebo Tests. And this is a co-authored talk with a co-authored paper rather, with F. Daniel Hidalgo at MIT. Erin's talk will last between 30 to 40 minutes, after which point we will take questions from the audience. You can ask a question during this, using the Zoom Q&A button that appears at the bottom of the webinar window. You may ask questions at any time during the talk, but all questions will be held until the end of the presentation. A link to Erin's paper and slideshow will be available in the Zoom webinar chat window so that you may refer to it throughout the presentation, and I will post those links right after we get started. And now I'd like to welcome Erin Hartman to the IMC. Erin, welcome.
Great, thanks, Justin. I'm really happy to be here. I'm going to talk today, what's the alternative? We'll start with a little stats joke. I'm going to talk about equivalence testing as an approach to balance and placebo tests. And as Justin mentioned, this is joint work with Danny Hidalgo over at MIT. So without further ado, we'll get started. So the main question that we're trying to answer is, as kind of causal inference has seen an increase in the social sciences, there's been a big emphasis on how do we judge the quality of our causal research design. When we don't actually conduct randomization as the researcher, or we don't know what the actual randomization mechanism was, we can never actually prove that our design is unconfounded, which is the core identifying assumption for most causal designs. But oftentimes we know that our identification strategies, whatever causal research design we're using, have some sort of observable implication in the data. And I'll talk more about what those observable implications look like. But most designs lend themselves to these types of tests that we can conduct, and we use these tests, these observable implications, to provide evidence that our design is a strong design, that we believe our identification assumptions. And so we're going to call these tests of design. Sometimes they're referred to as falsification tests. There's lots of names for it. And so what do I mean? Most causal designs, as I said, have implications about either the exchangeability of a group. So if we have a natural experiment where we believe something is as if random, then we believe that there should be some sort of balance on observables. We have to define what balance means, but we should, the implications that of as if random would be that the joint potential outcome distribution would be equivalent. And so if we look at pre-treatment covariates, those should look roughly the same, the distributions of those pre-treatment covariates between these treatment and control groups. Similarly, when we conduct matching, we believe that we should see balance on observables, and the hope is by our identifying assumption, we also achieve balance on unobservables, which we can't test. Other causal designs have kind of similar observable implications. So if we conduct a regression discontinuity design, our identifying assumption is continuity in the potential outcomes. And so we can, we should see continuity in any sort of pre-treatment outcomes. If we do difference in difference or some sort of synthetic matching, we should see some sort of similar pre-treatment trend between our treatment and control groups. And so when we talk about tests of design, what we're trying to check is these observable implications. We can check if these are empirically true, right? So we can never prove unconfoundedness because we can't check the joint distribution of potential outcomes or continuity of both potential outcomes in RD. But we can test these empirically, these observable implications using what we call balance tests, placebo tests, or like I said, sometimes called falsification tests. So I'll talk more about what these look like. Right, so what am I talking about? So say we have some sort of data where we've got 4 variables, 2 observable variables, x1 and x2, and we have unobservable variables, which obviously we wouldn't observe, but if we had some sort of oracle property here, we're going to look at. And what we see is that in the treatment and control group, we don't have balance, right? The distributions don't look the same between our observable pre-treatment covariates, x1 and x2. So we conduct some sort of matching method. In this case, I've matched each treatment to a similar control based on these observable pre-treatment covariates. And what you get is that I can make these observable covariates look very similar in distribution. Our identifying assumption hopes that the unobservable covariates look the same. It's hard to say, what this is just kind of showing why we can't ever prove unconfoundedness. Unobservable X3 is really important is highly, a strong prognostic variable. In some sense, we've made the balance worse. Have we induced some sort of bias? Is there remaining unconfounding? We'll never know. But what we can check is that have we met the criterion for observables? Have we made the distributions look the same? And we could check this across a bunch of observable variables. Similarly, for difference and differences, we're asking, if we look at our before period down here, are these 2 points similar enough? Or if we had many different pre-treatment periods that we had measured, are each of the points similar enough? Do they look like a similar trend or a similar starting point for a difference and difference analysis? For synthetic matching, which is related to difference and difference, we're asking, do the pre-treatment treated group and our synthetic control pre-treatment have similar trends? And finally, for regression discontinuity, what we're looking at is we want to know is on this pre-treatment covariate, when we say it's like the previous outcome, we will compare that to our forcing variable. Do we see that the line looks pretty close to continuous? If we're estimating these 2 lines on either side of our discontinuity, there might be some noise in the estimation, but can we show that they're sufficiently close to continuous? And there's other kind of observable implications. So a lot of times we talk about placebo outcomes. There's not a necessarily clear definition between balance tests and placebo tests, but typically we think of placebo tests as when you believe there should be some sort of known effect, usually a null effect, on a post-treatment outcome. There's falsification tests, or another kind of name for this, but you see falsification tests, say for IV, where you should see no effect on some related outcome of your instrument. It's related to the negligible effects literature, and I'll talk a little bit more about that, where I mean negligible effects, meaning your theory posits that there should be a substantively inconsequential, very small effect, some effect close to zero that you would say is effectively zero. And you can also use these tests in randomization tests when you conduct an experiment. So if you're doing re-randomization, this is a good measure. It's certainly not testing your unconfoundedness, because by design that will be true, but it's a nice metric for measuring balance. But if you're conducting randomization, or if you conduct an experiment and you want to measure an outcome where your theory posits that the treatment should have no effect on that outcome, you can use randomization tests to conduct exact tests for these placebo or negligible effects on an outcome. So what is the statistical problem? So the emerging norm out of the causal inference literature has been only if the empirical implications of our causal identification assumptions are borne out in our data, should we believe that our causal effect estimates are believable or unconfounded, and we can treat these estimates as true causal effects, right? And we argue that test design should be structured so the burden of proof lies with the researcher to try and positively demonstrate that their data is consistent with these observable implications of the identifying assumptions. And I'll talk a little bit about current practice, but what we see mostly nowadays is that people use statistical tests where they set up their null hypothesis that there is no difference, and they consider evidence of equivalence if they fail to reject that null of no difference. And this is, of course, not how the test of difference is set up. It's not meant to be interpreted that way. We teach in our intro regression classes that we should how to interpret p-values, and it is not to say that a large p-value is evidence of our null. And so we are incorrectly, as well as states, kind of equating a non-significant difference with significant homogeneity. And what we want to show is significant homogeneity. And so what we're going to propose is that we should begin with the initial hypothesis, kind of flip this around. This way I ask, what's the alternative? Our null hypothesis should be that the data is inconsistent with the observable implications of a valid research design, and we should only reject this null, that our data is problematic, if we see sufficient evidence. So I'll talk a little bit about current practice and how people seem to be conducting balance and placebo tests currently. I'll talk then about our proposed solution, which are equivalence tests, which we see in the bioequivalence literature, and I'll talk about how those tests are structured. And then I'll spend time talking about how to actually conduct an equivalence test for these tests of design. I'll give a couple examples. I'll talk a little bit about the relationship to this recent literature on negligible effects in authenticity. So what is the problem? Once again, we can never, and I can't emphasize this enough, we can never directly test unconfoundedness. There's no direct test of usually of our identifying assumptions. But as we see in the Edmonds and Rubin's book, if we see violations, they claim that an unconfoundedness assumption should be viewed as less plausible in cases that are not supported by the data. So how much of these results change our analyses, change our assessment of unconfoundedness depends on specific aspects of the substantive application at hand, in particular the richness of the set of pretreatment variables, their number, and their type. So what they're arguing is that if you can show evidence that many pretreatment covariates and many important prognostic pretreatment covariates show equivalence, then that's evidence in favor of your design. So since we can't directly test unconfoundedness, we argue that the statistical test should be set up with the null that the data are inconsistent with the observable implications of an unconfounded research design. What does that mean? That means something like they should be inconsistent with the idea of similar distributions or similar means, versus the alternative hypothesis that the data is consistent with the observable implications of an unconfounded research design. So by doing this, we're encoding what we usually tell our students to do is statistical skepticism, right? We want to provide evidence to disprove to provide evidence against our null. But the current practice generally looks something like we test if the mean in our treatment and control group are equal under our null versus the alternative that they're not. We argue that evidence of equivalence tests, the evidence of equivalence, there is evidence of equivalence if we fail to reject at some nominal level. And usually people kind of internalize that this is an incorrect interpretation of this test because we usually look for p-values that are more than just what we would usually call statistical significance. So not p-value 0.05, but rather p-values up around 0.2. And the problem with this is that there's a temptation to conflate often low power with equivalence. So we get a low power test, we get a large p-value. And even if we have a large substantive difference, we say, well, it's not statistically significant. And so that's evidence of equivalence. And that would be an incorrect interpretation of that test, but it's tempting to interpret it that way. The kind of flip side of that is that when you have a lot of data, you might, say that there's there's a statistically significant difference, even if that statistically significant difference is substantively inconsequential. And so what does it kind of look like? Here's an example of what these, kind of balance tests, a standard way of people presenting balance tests. This comes from Devin Coy and Jeff Secon's election discontinuity design. And what they're looking at is everything below the dashed line here. All of these are p-values on pre-treatment covariates using a difference in means test. And they say that there's, observable imbalance. And that, for some variables over here, p-values are large, maybe they're balanced, but some other variables are not. And of course, it's concerning if we see significant difference. The bigger problem is how do we interpret these large p-values? There's not really evidence that there is equivalence. And so as Fisher said, every experiment may be said to exist only in order to give the facts a chance of disproving the null hypothesis. By setting up our test this way, we're not really giving the data a chance to do this. And Andy Gelman says in social science, the null hypothesis is almost certainly false, right? So we want the null to be something that we believe to be untrue. You don't need a p-value to tell you this. P-value tells you the extent to which a certain aspect of your data are consistent with the null hypothesis. A lack of rejection doesn't tell you that the null hypothesis is likely true. Rather, it tells you that you don't have enough data to reject the null. Right? So this is kind of the main problem here. This lack of rejection doesn't tell you your null is true. And so what do equivalence tests do? What is our solution to this problem? It's to flip the hypotheses. So we want to start with a null that our data is inconsistent with these observable implications. So we operationalize that as saying, the difference between the treatment and control group is less than some lower bound or greater than some upper bound. Of course, it's going to be really important how we define those bounds, but we say it's outside of some consequential range versus the alternative that the difference is within this kind of inconsequential range that we define by this epsilon lower and upper. Right, so once again, our test of difference part of the problem is, of course, that they're set up to control a type 1 error where we reject the null, in this case, of no difference, even when a difference exists. It's not the type 1 error that we want to control for. And so how do you conduct an equivalence test? Usually, this is an example of what we call a two one-sided test. We set up some range where we say, we conduct these two tests corresponding to our two different null hypotheses over here. And we say if the difference lies within some range, we pick symmetric equivalence range somewhere around 0, right? So our difference is 0. We're going to get a low p-value on both of these tests, and we pick the larger of the two p-values that we observe. And if that larger of the two p-values is less than alpha, then we reject this null of a consequential difference in favor of the alternative that there is no consequential difference. And so now we're controlling for a type 1 error that's consistent with that hypothesis that I initially set up, that we want to start with the assumption that our data is inconsistent with a valid research design. So that's these are the two nulls that are inconsistent with valid research design. And our alternative is that the data is consistent with these observable implications. Of course, we're not the first people to come up with this idea of flipping the null. It has a long tradition, particularly in biostatistics. So it came out of the idea that if you're the FDA and you want to approve, is a generic drug performing the same as a name brand drug that went through FDA trials, it's not enough to show that there's no statistically significant difference. You want to actually try and control the probability that you falsely declare two drugs equivalent, therefore release a generic drug if it's not working as well. And so, this was born out of that literature. And there's been some recent adoption in political science. In particular, most related to this is the idea of negligible effects, which came out of an AJPS article by Rainey in 2014. And so there we're trying to, the goal is for a researcher to show that an effect that they observe is, not substantively significant. It's also related to some work on substantive significance by Gross and our host here, Justin. And I believe there's another co-author there, Donovan, that I apologize I don't have on the slide. And there, the goal is to show substantive significance, that our effect is, not only is it statistically significant, but the effect size is likely large and something that we care about substantively. And so those are related to this idea of equivalence testing. And so when I say there's a temptation, of course, we know that falsely, it would be incorrect to interpret a large p-value as evidence of equivalence or a lack of a difference in means if we're doing a difference in means test. But there is a temptation, right? So there's a good example that came out of Kosuke and Mai and some co-authors, and showing that, here we're declaring something non-equivalent. So here we're starting with data that is imbalanced, right? So test a difference p-value in this data set is highly significant. So our treatment and control groups look very, very different. And what they do is they randomly drop some percentage of the controls, right? So in expectation, we're not making balance any better. And if we're declaring something non-equivalent based on this p-value, and if we declare something, in that case, equivalent, if we fail to reject, by simply dropping controls at random, we're lowering the power. And we're more likely, as we drop more and more data, to declare the group's equivalent, as provide evidence of equivalence. And that would be an incorrect interpretation, but one that we see a lot. And in this case, we're looking at a prognostic variable that, on the scale of social science, is correlated with our outcome at roughly 0.2 is pretty powerful. And so when we conduct an equivalence test, we do the same the same exercise, but because dropping data, lowering your power, is not going to actually kind of increase your p-values, the equivalence test, because of the way we've structured the null and the alternative, will behave as we would expect, right? That initially we would fail to reject our null of a difference with all of our data, right? So our p-value is very large. And dropping data is not helping our cause. Towards the end, we drop so much data that it kind of looks the same, but it's still pretty rare. So this is how we would expect our test to behave. We don't want just to come to a wrong conclusion or provide the wrong evidence based on just the power of our test. So I want to talk a little bit about how an equivalence test works. So to do this, I'll first talk about defining the equivalence range. That's that epsilon L and epsilon U that I mentioned. I'll talk about picking an appropriate test to do this. There's a bunch of different tests you can pick based on the type of data or your departures from the null that you want to test. I'll talk about conducting the test and obtaining a p-value and interpreting that p-value. And then I'll talk about looking at what we call the minimum credible equivalence range, or the inversion of this test, which is a new metric that we're talking about that is more objective, that researchers can look at and should look at when presenting these types of results. And then I'll end with a note on the power of the test. So let's start with, how do we define this equivalence range? Right? So I told you that you conduct this test, you do this two one-sided test where you say either it's below some lower level or above some upper level. So when we pick these ranges, certainly the best option that we argue, and a real value of these tests, is that you can define these ranges based on substantive knowledge. If you know that a variable is highly prognostic, is pre-treatment outcome, you might want to set a very, very small range on that, because you think that imbalance in that could cause a lot of bias. You can set variables that are less highly related, that you think wouldn't impact bias that much. You can give them a slightly larger tolerance. And you can set these on the scale of the variable and decide, what is enough to convince your reviewers and academic audience that imbalances in these range are inconsequential. Of course, we don't always know how to define these ranges based on substantive knowledge. So we also talk about a couple other approaches. One is a sensitivity approach. So similar to kind of how we think about sensitivity analysis. So we assume that the minimal range is one standardized mean difference of your outcome of interest. So whatever your effect size was, standardize that. And you set that as your range. And the idea is kind of, if there's a linear relationship between this variable and your outcome, that range would be enough to explain your effect. There's also literature out there about kind of defaults. So a 0.2 standardized effect range standardized range is considered pretty high bar. It's hard to prove equivalence within that range. A more lenient range is 0.36. The 0.2 range comes from some simulations that Rubin and some co-authors did, showing that under a set of assumptions, imbalances of that level don't induce a lot of bias. Right? And so one of the points that came out of the negligible effects literature is that this range can, in some sense, allow the researcher to signify the strength and confidence that they have in their research design and therefore in their claim, right? So if a researcher comes to you and they say, I set the range really, really wide, they made their test in some sense easier on them, versus if they made the range really, really small, then they've set the bar really high. And if they can pass the really high bar, then we should believe that there's more evidence in the strength of the design. Of course, how you pick that range is going to impact the power of your test. If you make that bar really, really high, you're going to need more data to be able to clear it. So once you pick your range, hopefully substantively, if not that, using one of these other methods, you have to pick an appropriate test. And so the kind of most common one that you see is called the two one-sided test. That's an example that I showed you. And so it uses something called the intersection union principle. And so the idea is that you have a set of null hypotheses. Your null hypothesis is the union of these null hypotheses. And the alternative is the intersection of the complement of these hypotheses. So what does this mean for for the two one-sided tests, we start with a null hypothesis that's the union of it's either larger than our upper bound or lower than our lower bound. And then the complement of those two, the union of that is that our difference or our standardized difference is within this equivalence range. These types of tests are really good for when you're doing, say, mean difference testing of any sort. So matching, synthetic matching at some number of periods, looking for negligible effects, any sort of placebo outcome. And when you do this, you're going to get, a t-statistic corresponding to each of these one-sided tests, right? So your null is going to be centered on either this upper or lower. And we reject our null, that there is a substantively significant difference, in favor of the alternative that there is not if both of these one-sided tests reject at the alpha level. And what the intersection union principle tells us is that if we reject both of these tests at the alpha level, then our overall test will have the correct size. Right, so kind of what does that look like? So here's our two one-sided tests. The gray area corresponds to our rejection region for each test. If we observe a difference that's within the range, what does that mean? Well, on our lower test, alpha is greater than our p-value, right? Our p-value would correspond to this area to the right. On our upper test, our p-value corresponds to this area on the left. Both are less than alpha. And so we reject that there is a difference in favor of the idea that they're equivalent. If we see a difference that's outside of this range, then of course, our p-value on the lower test is very, very small, but our p-value on the upper test, which would be to the left of the blue bar here, is larger than alpha, and so we would fail to reject the null that there is a substantively significant difference. Of course, so this test, it's been shown if you use symmetric bounds, corresponds to basically conducting a difference in means test looking at the 1 minus 2 alpha. So if you want to test at the alpha equals 5% level, you look at a 90% confidence interval and ask, does that 90% confidence interval lie within the range, entirely within this equivalence range? It is not always the case that will be true, and that Berger and Shu article from 1996 kind of talks through more powerful tests, right? So this is not always a more powerful test, and depending how you set it up, given your sample size and given the range, the range that you pick, especially if you pick it based on substantive criteria and substantive findings, you can set yourself up for a test that would have zero power. And so what we actually talk about in the paper is the uniformly most powerful invariant test for equivalence. That's the t-test for this. And so this is, once again, good for difference in means, where if we're looking, say, at matching, difference in difference, some sort of negligible effect. And we set up our hypotheses the same way. Our test statistic is just our t-statistic, but our rejection rule is based on a non-central f distribution. So we take the square root of the non-central f and we compare that to the absolute value of our t-statistic, right? And so some of the extra power comes from acknowledging that when we do these tests around these two different nulls, we should use a non-central, t distribution. If we're using symmetric nulls, then we can look at this absolute value, compare it to the square root of the f. So what does that end up looking like? This is kind of our distribution holding the non-centrality parameters or equivalence range the same. You can see that as this is for kind of lower sample sizes. As sample size increases, our critical value is going to move further out, and we test rather than an F test where we would normally look at right tail here. For equivalence, we're looking at the left tail of this always positive distribution. Those aren't the only tests that are out there, right? So that's the equivalence T and the two one-sided tests I talk about. There's people have worked out if you care about the ratio of your outcomes as opposed to, say, difference in means. There's two one-sided test equivalence versions of that. If you have binary data, you can look at Fisher exact test. There's a Mann-Whitney test that we talk about that's good for testing distributional changes. It uses a rank sum. And of course, if you're in a world where you can use permutation inference, you can use permutation versions of any of these tests. And we've done some simulations, and it does seem to work pretty well, especially so if you're an experimentalist and you want to look at an outcome, once again, that you hypothesize should be 0, it wouldn't be sufficient to fail to reject that. Here you'd want to use a permutation version of say, a 2 one-sided test. And you just conduct your permutation tests, one-sided tests on those epsilon L and epsilon U, and it works pretty well. Right? And so why would you do this for the permutation test? Well, there is some concern out there in the literature that this balance is not, that a lot of times these tests refer to these hypothetical superpopulations, right? We're drawing our treatment and control group from these 2 distributions, and we're asking, are the difference in these 2 means the same? And that's not really what we have when we have an experiment. And so people use randomization inference because that's what's justified by the designs, type of design-based inference. The intersection union principle in the 2 one-sided test still applies here. And the nice thing is it'll allow us to test not only for changes in means, but changes in distribution. Right, so then we conduct our test, right? So we picked our test, we picked our range. Now we can conduct our test, we obtain a p-value. Of course, once again, the p-value now corresponds to rejecting or failing to reject a substantively significant difference at baseline. So if we get small p-values now, that's evidence in favor of equivalence, right? And this is what, as researchers, how we should set up a skeptical statistical test. So we now control the probability of falsely rejecting the null of a difference. The nice thing about setting up our p-values this way is if you're conducting, say, a battery of univariate tests, so a lot of times people want to look at balance on individual characteristics, but they want to look across a bunch of different characteristics, right? So once again, thinking about that initial balance plot that I showed you, we're looking at a bunch of tests. When we're conducting a bunch of tests, over all of those tests, we're not controlling the type 1 error rate. And so now these equivalence tests can directly be applied to using multiple testing corrections. So you can either look at the family-wise error rate, where we look at the probability that we've made at least 1 type error, or false discovery rate, which will control for the proportion of errors depending on which one is more important to you. You can use corrections for either type of error rate. And so this is nice so that, we can conduct omnibus tests. Omnibus tests should still be structured consistent with this framework, right? So our omnibus test should provide evidence, should start with a null that the 2 groups don't look the same. But if you care about univariate tests, you care about showing evidence that your most important prognostic variables show evidence of equivalence. It's nice to be able to control for these multiple testing. And anytime you're conducting a placebo outcome, right, some sort of theorized null effect, you should be controlling. If it's in your suite of outcomes, you should be controlling for the multiple testing problems. So last thing I want to talk about is the minimum credible equivalence range. So what is this? It's akin to a confidence interval. So we invert the test. And what it's going to do is specify, given your alpha, the smallest range that could have been supported by the data. Right? So it's invariant to your hypothesized equivalence range. So a big complaint about equivalence testing is that people, can arbitrarily pick an epsilon L and epsilon U. You pick a really big range, that'll make your p-value very small, but you haven't really made the bar very high. And so this credible equivalence range will convey what's the minimum range that the author could have chosen. And this is really where we think researchers should debate, is that range small enough, right? And I'll show you an example of what that looks like. A quick note on power. The power of the test, of course, is maximal if the true difference is 0. So here you can see from smaller sample sizes up to larger sample sizes, the power of the test. So our alternative here, of course, is true. It's maximal if the true difference is 0. This is fortunately what's hypothesized by many balance tests. But if you're looking at negligible effects, if your truth is very close to the bound of your equivalence range, you're still not going to have very much power. It's really hard to show effects that are very close to your equivalence range. But of course, as n increases, it gets you gain power. And these tests, it's really hard to show equivalence. You can see that here. So I'm going to talk about 2 really quick examples. So the first is Brady McNulty's 2013 paper. They exploited a natural experiment of polling places in LA. So the voters were reassigned, some of them, to new polling places. And they want to look at what is the impact of the physical cost of distance to the polling place. If your polling place was moved closer or further away from where it was before, what is the impact of that on turnout? They use a matching algorithm to match voters on a few important covariates they noticed small imbalances on. Of course, there's a ton of data here. There's all these voters in LA. LA is a very big county. And they report balanced statistics, right? So they report mean differences, but they on these variables they didn't use in the matching algorithm. So not just things they've mechanically made look similar, but things that they didn't include. And they say for the rest of the results, it does not make a great deal of sense to present t-statistics because the large sample ensures that most of the differences are statistically significant. Rather, we focus on their size. So they're very explicitly saying, we want to show that these effects are substantively inconsequential. And the difference in means test is not going to help us do that. We're going to see statistically significant effects just by the virtue of the size of our experiment. So what they observe, we're going to look at one important important outcome, which is the prior distance to the polling place, right? So you'd hope that at baseline, you treat those individuals that had their precinct moved and those that didn't look similar in terms of how far they had to walk before. And what they find is a difference of about 42 yards, or so half a football field. When we conduct our equivalence test, we use the sensitivity approach, right? So I don't know how to tell you what is inconsequential walk. I love walking. Maybe it's half a mile. Maybe you hate walking. It's 20 feet. We can debate that. So we're going to start with the sensitivity approach, and we look at a standardized effect on their primary outcome of interest, in-person polling place turnout. It was about 1.5 standard deviations, and so that amounts to about 65 yards, right? So we're going to set an equivalence range of 65 yards. We're going to test at baseline were these two groups more than 65 yards difference versus were they not? And we could construct this on substantive grounds. Is 100 yards inconsequential? Is a football field inconsequential, right? So as a researcher, you could argue this. We're going to start with the sensitivity approach. When we do this, we get a p-value of effectively 0. And once again, we have a ton of data here. But more importantly, if we look at the credible equivalence range, it spits out 49 yards. So the minimal range that could have been supported at the alpha equal 0.05 level by this data is 49 yards. And we think the real value of these tests is that we don't have to debate was 0.028 miles, the standardized effect approach, the right measure. What we should be debating is this 49 yards, sufficiently small that we believe that the design is likely unconfounded, or should we do further adjustment through regression or something like that? And we now have this objective number that subject area experts can discuss. And a quick final example, and then I'll turn it over to questions. So Dunning and Nalkani in 2013 look at a paper where they, look at a national experiment where they're trying to evaluate the effect of ethnic quotas on redistribution. And I want to discuss this because here we're looking at a suite of pretreatment outcomes. And they are leveraging this, the fact that quotas were implemented at different time periods using this ordered list. And so right above and below the cutoff for a given election, villages look very similar, right? So we want to test this. Do these villages look similar on pretreatment covariates? They present a bunch of evidence to try and to convincingly argue that this is a good, pretty sound design. And in one of those tests, they present a set of balanced statistics for univariate tests. They say the p-values are generally high, but there's a couple that are kind of inconclusive. I would say the number of households in a village, proxy for size of the village, I guess, has a p-value of 0.09. So once again, I think people usually we're not looking for p-value 0.05 on the tested difference. We want to look for p-value closer to 0.2 maybe, or there's no hard number, but maybe this is close to a consequential difference. And same with mean number of female non-workers, right, which had a p-value of 0.12. Of course, they present an omnibus test as part of their example and a series of other compelling arguments, but I want to focus on these two. So here we've presented kind of how we think balanced tests, especially if you're doing a suite of balanced tests, should be presented. So we look at all of their pre-treatment covariates, and the variable is here on the left. The observed mean difference on the scale of the variable is presented. So how big is the difference? Here we tested the equivalence range at plus or minus 0.36 standard deviations. The smallest standardized effect size was 0.43. So this is a more strict criterion than the sensitivity test would have been. And what's presented in black is the actual difference. And gray is the credible equivalence range, so that minimal data supported range. And we've converted it back to the scale of variable. This is in the standardized differences. The scale of the variable is presented over here. So number of households, there are 99 fewer households in the treatment group. We could have supported an equivalence range as small as 210 households. And then finally, we show the false discovery rates, since we've conducted so many tests, the p-values. And so we see that all of our p-values are below our nominal level, 0.05. So as evidence, we argue that there's balance on all of these characteristics. So once again, we think an advantage of the credible equivalence range is rather than arguing over should we have used 0.36 standardized differences or the sensitivity approach, right? We can actually just ask, is plus or minus 210 households on this number of households an inconsequential difference? And our p-values can also be adjusted to account for the large number of tests we conduct. So with that, I'll conclude. Once again, without researcher-conducted randomization, we can't ever prove unconfoundedness, but we want to provide evidence that our design is strong. And so tests of design should be structured, so the responsibility lies with the researcher to demonstrate that their data is consistent with their identification assumptions. And we encourage researchers then to begin with the assumption that the design is flawed, that the data is inconsistent with the observable implications of their research design, and that only kind of reverse this conclusion if they find sufficient evidence. And so that implies that our null should be one of non-equivalence. We show that equivalence testing are not as susceptible to the temptation to conflate low power with evidence of equivalence, which we see a lot of now. And we require, by requiring researchers to specify their ranges ex ante, we can have debates about substantively and consequential differences. And it really emphasizes and focuses on that. We can do that both through the way that researchers structures the test and through these credible equivalence ranges. We're working on an R package that'll have a suite of all of these tests. We're looking at extensions to omnibus tests and kind of multi-dimensional tests. We're looking for specific causal design tests, so the tests for continuity, tests for distributional equivalence on pretreatment, trends and stuff like that that apply to each causal design. And hopefully that package one day will basically take in your causal design and return the appropriate equivalence test. Thank you so much.
All right. Thanks for Erin for that presentation. Oh, I just messed up my script. Thank you, Erin, for that presentation. At this point, Erin Hartman is available to take questions from the audience. You can ask a question using the Zoom Q&A button that appears at the bottom of the webinar window. And as an experimentalist and a methods person, I'm really interested in this project. So the first thing I wanted to ask, we recently had Diana Mutz as a speaker in our department. And she was talking about, she actually didn't give a presentation about this paper, but she talked about this paper. Have you seen this paper in the American Statistician?
The one that says don't do balance tests?
Yeah, that's the one. So, I mean, I was looking it up as you're giving your talk. So, she says, and I should clarify, this is with a couple of co-authors as well. Confident, if you basically do balance tests and then try to adjust for covariates that are unbalanced, they claim confidence statements are wrong, the wrong statistical model is chosen, absolutely any result can be obtained when there are sufficiently many covariates, and it can easily lead to a false boost that pushes the p-value over a threshold such as 0.05. So I know this is not this is not an author meets critics panel, but I'm wondering what you think about these criticisms.
So my take is that, one, that's why I very specifically So there's two things. So in the paper, we talk about this more. The kind of interpretation, if you're an experimentalist, should not be one about whether or not your design is unconfounded or not. There's kind of a literature that talks about interpreting these p-values as one of metrics of balance, and I'm trying to look it up because somewhere there's a really great quote from Rubin for, I think, Fisher via Cochrane, that basically says that, he asked Fisher, would you re-randomize? And Fisher says, of course, if I saw that pre-treatment covariate, I believe it was Fisher, pre-treatment covariate was severely imbalanced, a highly prognostic one, I would re-randomize. And I guess my take on it would be, if you account for that re-randomization scheme, right? So if you use re-randomization and you derive your permutation distribution or your randomization distribution, given how you actually chose your sample, right? So your p-value should still be correct if you're not erroneously thinking that all possible randomizations were plausible or possible in your sampling distribution, but you take out those that wouldn't have met your criterion. And so if you're re-randomizing and you're not encoding your metric very directly into your randomization scheme, yes, I agree, your p-values could be wrong. If you are encoding it, so this is a nice way, I believe, to encode it, is like, I'm going to enforce, certain threshold criterion on maybe all the same or differential based on how prognostic I think a variable is, but you can account for it, by re-randomizing, and you can apply that same scheme when re-randomizing to construct your permutation distribution for any outcomes as well. And so I think that, we do, unbiasedness is a property of repeated samples. We get one draw. I think experimentalists are right to be concerned about whether or not, not whether their design is unbiased and their estimator is unbiased, but rather whether or not that specific estimate they get, given they are only getting one draw, is particularly close to the truth. And so, I think that these types of adjustments are warranted under that scheme, but you need to account for that re-randomization or whatever criterion you're using when constructing your p-values.
Yeah, I mean, I guess that my reaction to that is anytime I'm, the causal inference movement, if it's about anything, it's about relying more on the strength of design and less on the strength of models or theories. Yeah. And what you just said was the opposite, right? You said, well, the design may or may not be valid, but you've got particular data that are perhaps representative of an extreme draw, and so we ought to intervene on that.
I guess I'm not saying that the design's not valid. I think that the design, if you randomize, your design is unconfounded. You're not trying to, and I'm saying this re-randomization should be pre-treatment, right? So if your criterion was, I would not have picked anything where I saw a large difference on my most important covariate, pre-treatment covariate, then that should not be eligible in your sampling distribution for your outcome. Those were not possible.
Well, what I'm saying is, I didn't mean to say that you were saying the design was invalid. What I'm saying is your procedure is now design plus some kind of model, right? It's design plus modeling of the outcomes, because you've got a model of balance, and you're choosing according to what that model tells you. And I'm actually a person that's okay with models generally, but if I'm really a strict causal inference kind of person, I'm going to say something like, all that uncertainty about balance is built into for example, into the confidence interval. In other words, it's built into the design and in the estimators that flow from that design. And any kind of mucking with that is getting back to regression land, in some.
But that's not true. If I, just like saying I'm going to do complete randomization versus binomial randomization because I want there to always be an equal treatment and control group. I've taken all possible treatment assignments and I've changed my sampling distribution down to only those that where some set number of individuals are assigned to treatment and assigned to control. And design-based inference, I can use design-based inference to conduct an exact test under a strict null using that sampling distribution. By that same logic, if I say I'm going to also not allow those in which I see severe imbalance on my most important prognostic variable, those are not eligible. I would not assign those treatment vectors. I can remove those from my sampling distribution. That sampling distribution will still be, it's still valid. I can still come up with a permutation test that will, that meets that would recover that sampling distribution. And it will just enforce that, there is not severe imbalance on some prognostic variable, and that any estimator that you use would still be unbiased in that world. It's just reducing, hopefully, if you pick a good prognostic variable, the variance of that sampling distribution.
I'm wondering about so a lot of the the canonical statements of, why experiments are good, right? Why experiments work. They may not necessarily be all asymptotic, but they do rely on they rely on certain laws of large numbers, right? You have to have a certain, it's a bad idea to take 20 subjects, divide them into two groups of 10 and say, oh, I randomized, so everything's fine, right? You need a certain critical number. So I'm wondering the extent to which these problems with balance that you're pointing out are less relevant as sample. In other words, let me ask this question in a more provocative way. Does this all go away if we just get better about running highly powered experiments with enough people in them?
I mean, I think what we find is that you will come to a substantively different kind of argument, right? Like, do you say that there's evidence of equivalence or not? If you have a very small sample size, probably, if your criterion was, did I have statistical significance on a test of difference versus a test of equivalence, you're going to get very different answers. At the flip side, if you have very extremes, the difference you would get here is one of, if you had, like in the Brady-McNulty example, a ton of data, you're going to end up in a world where you're going to find everything statistically significant using a test of difference, but those differences aren't consequential. And what the equivalence test is going to do is allow you to encode substantive significance, and what is a consequential difference and what is not. In practice, I think that if you have kind of sufficient data, you're not. This isn't going to, because people kind of had already encoded that they wanted p-values not of 0.05 but rather of 0.2 or higher, right? Like that kind of intuition seems to kind of conform with what we would say. And like we saw in the Dunning and Nalkani example, that p-value of 0.09, which was kind of close to making us uncomfortable, in the equivalence test gave us a p-value of 0.04, which again, barely maybe evidence of in favor of equivalence. But so kind of in middling examples, you probably get similar answers. Sometimes it'll be different, sometimes it won't. I think that by setting up the test this way, and this is different from an experimentalist, right? Like if you're not an experimentalist, you do need to provide evidence of the strength of your design. Mm-hmm. And I think this forces us to look at what do we think is too much imbalance, and we need to encode that some way. And the p-value approach we've been using on test of difference is not doing that. And we see the problems of it both directions. Either people not really thinking about what is the implied substantive significance because they have not enough power, or focusing only on the substantive significance anyway because they have large power. And if you have a lot of data, your equivalence test will allow you to make a very tiny equivalence range, and that credible equivalence range will be very small, and that's even more evidence in favor of your design.
One thing I was thinking of when you were talking during your talk, is there's this paper by Kevin Clark the Phantom Menace paper about whether it's a good idea to control for variables or not. And essentially what he says is, yeah, if you get the model right, then yes. But if your model is partially right, which is almost always, then the answer is much more ambiguous. Introducing controls can actually make things better or worse. And it strikes me that there might be a similar way of thinking about this paper. If I have a set of covariates, which is obviously an incomplete set, re-randomizing may or may not cause problems, but often if I have a lab experiment, I can't do that. So I'm not, at least not cost effectively. So what I have to do is I have to control, right? I have to introduce controls to try to eliminate the bias. And that may make things better and it may make things worse. And I'm wondering how your procedure will do if you're trying to perform balance tests on an incomplete set of covariates, which were all correlated with each other.
Once again, it's important to separate your goals as an experimentalist versus an observationalist. So most of what we're talking about in this paper in terms of interpreting the p-values as evidence is for observationalists. For experimentalists, once again, I would say, like, if you observe a large imbalance in your sample, that's not bias. Bias is an estimator property. Your estimator is unbiased. That's estimation error in that sample. And I would point you to Winston Lynn's paper, and the kind of best way, of course, it relies on asymptotics, but the best way to control for imbalances and the proper forms to do it, to still retain an unbiased estimator that might have some finite sample problems, but asymptotically will be good. And so I think the tests, the way that our test plays into that, I guess, would be just, are you using this as a metric of, possible large difference? It's not a question of imbalance of your design or confoundedness of your design if you're an experimentalist, but just, a large difference of, that you got a bad draw on that pre-treatment covariate, and whether or not that's worthy of controls. I would turn to that decision, right? Because this is no longer, you're not interpreting this as say a statistical test so much as a metric. How you use that metric and whether or not you decide to pursue regression adjustment, say, to your experiment, you should be kind of tied to that literature on regression adjustment to experiments. And I think the Lynn paper would say that so long as you use a fully interacted model with the correct standard errors, then you have nice properties, even that retain kind of the value of the randomization, but still allow for precision gains.
Well, we are out of time. It is noon, at least where I live. So first, I'd like to thank Erin Hartman for being our presenter this week. I want to point out that her presentation will be posted to our website shortly after this broadcast if you'd like to share this presentation or watch it again later. I also want to invite everyone to join us on Friday, April 13th, when we will host a talk from Michael Bailey of Georgetown University. The talk is entitled Designing Surveys to Account for Endogenous Non-Response. Please see our website, www.methods-colloquium.com, to get more information about this talk. And Erin, thanks a lot for giving the talk today.
Thank you.
All right, and I hope to see everyone on the 13th.